Hello everyone. Today we'll be covering a queuing theory question commonly seen in INDU 211. So let's read through the question together and then solve. The question states that a takeout fast food restaurant located in a busy downtown area has one window open from 11 a.m. to 11 p.m. each day. So that's a 12-hour period. We know that right away. It is found that every 10 minutes in average, there is a customer coming to the restaurant, which means that the arrival rate is going to be one customer every 10 minutes. The average time to serve a customer, including the time to place order, time to get food ready, and time to pay the bill, is 4 minutes. So we could say that that is our average or mean service time per hour. It is also observed that both arrival and service processes follow Poisson distributions, and we're asked to use the standard queuing theory models discussed in class to evaluate the situation of the restaurant by calculating the following four. 5.1, the estimated time that the service window is busy serving customers in the 12-hour period each day. The expected time a customer will wait to get served after he or she arrives at the restaurant. 5.3, the expected time a customer will spend at the restaurant, including waiting time and the time of being served after he or she arrives at the restaurant. And finally, 5.4, the estimated time that there are two or more customers in the restaurant in the 12-hour period each day. So we can use these equations that are also provided in the question for system utilization, expected time in queue, expected time in system, and probability that there are n customers in the system. For most of these types of questions, when the equations or the formulas are given, it's a lot of plug and play. Before we get started though, we should first figure out our values for lambda, which is our arrival rate of customers per hour, and our mu, which is our mean or our average service rate of how many customers are being served per hour. So we should do this before attacking and trying to tackle questions 5.1 through 5.4. So if we have that one customer arrives every 10 minutes per 10 minutes, we can assume that in 1 hour, the number of customers that will arrive can be described as 60 minutes, which is 1 hour, divided by the arrival rate, which equals to 6. This is customers per hour. This also gives us our lambda. Now, for our mean service rate, we have that one customer can be served in, on average, 4 minutes. So if we have one customer served in 4 minutes, right? This is on average. We can describe the mean service rate as per hour as 60 minutes, which again is how many minutes in 1 hour. We want to convert everything to hours as the question is dictated in hours. 60 minutes divided by 4 minutes per customer equals 15, 15 customers that are being served every hour on average. So this gives us our mu. So now let's use our lambda equals 6 and our mu equals 15, right? Our arrival rate per hour and our mean service time per hour to calculate questions 5.1 through 5.4. 5.1 asks us to calculate the estimated time that the service window is busy serving customers in the 12 hours each day. This is very simple. We can just plug in our formula for system utilization, which is going to be P equals lambda over mu. Now this is for 1 hour. In order to get it for the entire 12-hour duration, we just have to multiply each side of the equation by 12. So 12 times P is going to be 12 times 6 over 15, which is going to give us, 4.8 hours. And this is how the estimated service time, the estimated time that the window is busy during the 12-hour period. So for question 5.2, which we can do down here, we're asked to calculate the expected time a customer will wait to get served after he or she arrives at the restaurant. So here we can use our formula for expected time in queue, which is described in the formulas provided in the question as TQ, time in queue, equals lambda over mu times, in parentheses, mu minus lambda. And this is going to give us 6 times 15, in parentheses, 15 minus 6. And if we compute this value, it's going to give us 0.044 hours, or TQ is going to be approximately 2.7 minutes. If we wish to get a more realistic idea of what this small fraction of an hour is. For question number 5.3, pardon me. For question number 5.3, we're asked to calculate the expected time a customer will spend at the restaurant, including waiting time and the time of being served after he or she arrives at the restaurant. So here we can use our formula for expected time in the system. Let's go ahead and write this over here. 5.3. So our formula for expected time in the system, it's once again given in the question. It's going to be TS for system, time in system, equals to 1 over mu minus lambda. And when we plug in those values, we're going to have 1 over 15 minus 6 equals to 0.11 hours. Or, once again, since it's a fraction of an hour, we can convert to minutes by multiplying by 60 to get 6.7 minutes. So this is the expected time in the system. So question 5.4 asks us to calculate the estimated time that there are 2 or more customers in the restaurant, in the system, in the 12-hour period each day. To do this, we need to first estimate the time that we need to find the estimated time that there are 2 or more customers in the restaurant by first finding the probability that there are 2 or more customers n in the system. So we have to find out the probability that n, the number of customers in the system, is bigger than or equal to 2. We have to use the Poisson distribution, as that is the way that this is distributed, as mentioned earlier in the question. And the formula for the Poisson distribution probability is given once again in the question. So we need to find out the probability that n number of people in the system is bigger than or equal to 2. So to do this, we can use our Poisson distribution probability formula for Pn equals 1 minus lambda times lambda, 1 minus lambda over mu times lambda over mu to the power of n. Now, in general form, what we're looking for when we talk about probability, we typically write it as such. This means that we're looking for the probability that n number of people in the system, in this case, is bigger than or equal to 2. Now, because there's no possible way of calculating possibilities that, or probabilities rather, that there are 2, 3, 4, 5, all the way to infinity amount of people in the system. The way to calculate probabilities for a range from 2 to infinity, or anything to infinity, is by subtracting all other possibilities from 1, 1 being 100% probability. So in this case, it would be 1 minus the probability that n is smaller, exclusively smaller than 2, as 2 is part of the range from 2 to infinity, as shown here. So this is going to give us the probability that there are 0 people, that there is 1 person, and that's it. We need to consider 2 scenarios. One scenario when there are 0 people in the system, and one scenario where there's 1 person in the system. So let's continue expanding this and writing this out. So here we can look at it as such. 1, which we have from over here, and then we need to expand this into the 2 parts that are within this range smaller than 2, which is going to be, in big brackets, P of n equals 0, so the probability of there being 0 people in the system, plus the probability of n equals to 1. So this is going to cover all of the options that it's outside of the range from 2 to infinity. We subtract that from the total possible probability, which is 1. 1 equals 100% probability. And then we get our probability for n equals 2, 3, 4, however high it goes. So let's keep expanding this and filling in all of the values for lambda, for mu, and for n. So here we're going to have 1 minus, and then we just fill in this formula for 0 and for 1. So this is the formula that we fill in for 0 and for 1. So for 0, it's going to be 1 minus 6 over 15, right? Lambda over mu, times lambda over mu, 6 over 15, right, as we saw here, to the power of, what does n equal in this case? It equals 0. So this one's very easy. This was just going to equal 1. And then we just have to compute that, as the exponent is 0. And now we have to do the exact same thing, this time for 1 over 15. 1 minus 6 over 15. Once again, everything stays the same for this part. Then it's 6 over 15. And now n, in this case, equals to 1. And we close off our big brackets. So once we calculate this entire expression over here and subtract it from 1, we should get a probability of 0.16 that there are 2 or more customers in the system. But the question asks what is the probability that there are 2 or more customers in the system during the 12-hour period. So as with everything else we did previously, this is the probability, since everything is per hour, those are our units. It's 6 customers arriving per hour, 15 customers being served per hour. This is the probability that there are 2 or more customers in the systems within 1 hour. So to get the estimated number of customers for the entire 12-hour period, we need to multiply this probability by 12 hours. So we can go ahead and do that down here, and it's going to be 0.16 times 12 hours, and that is going to give us an estimated 1.92 hours. So we multiply the probability that there are 2 or more customers in the system every hour, and then we multiply that by the number of hours in the 12-hour period, which is 12, to estimate how many hours per day there are 2 or more customers in the system. And that gave us 1.92 hours. So in total, 1.92 hours each day, there are 2 or more customers in the system.